Hello everyone, and welcome back to the fourth and final day of related rates. Today we're going to cover two different topics. We're going to talk about rates of change of angles and also similar triangle problems. Alright, so the first two problems that we're going to tackle today deal with finding the rates of change of angles. And we want to make sure that we are keeping some hints for you is that whenever we draw these, we are going to be drawing right triangles, and you're going to see that as we draw the pictures. And so we're going to be using right triangle trig. You're going to remember that good old-fashioned SOHCAHTOA that you should know from, I don't know, what, 7th, 8th grade? All right, so number one says, Dorothy, who is standing at point A, watches the professor and the balloon rise straight up from point C. Dorothy is 80 meters west of point C. The balloon is rising at a constant rate of 5 meters per second. Find the rate of change of the angle formed from Dorothy's line of sight when the balloon is 60 meters off the ground. All right, so the first thing I want to do, obviously, is get a picture of what's happening here. Okay, so we're talking about these points A and C and Dorothy and the balloon. And so we want to start, there are some key sentences in here that kind of tell us Dorothy is 80 meters west of point C. All right, so I'm going to start with the point C, and that's where the balloon seems to have been launched from. Dorothy is 80 meters west of that. So this is 80. Okay, so this is where Dorothy is. All right, now the balloon rises up from point C straight up. So that would be where the balloon is. Okay, so B for balloon. And it tells us that it's rising at a rate of 5 meters per second. So let's get some variables on here. Okay, we're going to go ahead and we'll call this side A and this side B. And we're going to finish off our triangle and make this side C. All right, so if they're giving me the rate at which the balloon is rising is 5 meters per second, rate, remember, is derivative. So that's your dA dt equals 5 meters per second. Okay, and this was 80 meters over here. And then it told us to find the rate of change of the angle formed from Dorothy's line of sight. Okay, so where is the angle that they're talking about? Well, clearly it's not the right angle. Okay, where's Dorothy standing? Dorothy is standing right here, okay, and she's looking up to this balloon. And so that is the angle that they're talking about, this angle right in here. And they are asking for d theta dt, the rate of change of the angle, and that's what we're looking for. Okay, when the balloon is 60 meters off the ground. So when the balloon is 60 meters from the ground. All right, so now we know two of the sides. We know the rate of change of the balloon. And so we have a right triangle. The first thing I'd probably want to do is find all three sides if I can. So if I know two sides, I certainly can find the third side. Okay, and if you look a little closely at these numbers, we have 60 and 80, and we should recognize that those are actually multiples of the 3, 4, 5 triangle, or you might notice the 6, 8, 10 triangle when you're looking at these. And so C is actually going to be 100 meters. Okay, so now I know all three sides. All right, when we tackle these problems, the first thing I really want you to think about with these, and it's going to be really important, it's going to help you set these up with so much more ease, is there a constant? Okay, so we want to ask ourselves that question. Is there a constant in our picture? Is one of these sides constant? So the way you kind of answer yourself that is if they give you a rate for the side, it's not constant. So clearly, side A is not constant. The balloon is still moving. Okay? If you kind of go along that train of thought, side C is also not going to be constant because the balloon is rising. And so B is attached to that side, so that is not going to be constant. But they did tell us that Dorothy is standing. She's not walking. Dorothy is standing 80 meters west of point C. So this here is, in fact, a constant. Okay? So this, side B, is constant. And that is so important. Okay? And that makes us happy when we have a constant. All right. So now the next thing you want to do is we want to choose a trig ratio. Remember we talked about this is an angle here, and we want the rate of this angle. Well, we have a right triangle, we know all three sides, and we're looking for the rate of change of an angle. And so we're definitely going to use one of our sine, cosine, or tangent. All right, how do we know which one to choose? Well, we have all three sides, so it seems like we could choose any of them. Well, I will say, first of all, we want to use our constant. So use the constant in the trig ratio. Okay, so we definitely want to use side B, which side B is the adjacent, okay, to the angle. So we definitely want to use side B. Now, what other side do we want to use? Well, it just might make most sense to use the side that we know the most about. Well, which of these other two do we know the most about? We definitely know the most about side A because we not only know its length, but we also know its rate of change. So we're going to go ahead and build a trig ratio that uses the side B and the side A for this angle. So if you remember back to building basic trig ratios, okay, in a right triangle, side B we said was the adjacent, side A was the opposite. And so which trig ratio uses opposite and adjacent? Hopefully you are saying tangent, okay, and then you would be correct. Okay, so we're going to go ahead and write that trig ratio. We're going to say tangent of the angle is equal to opposite, which is side A, over adjacent, which is side B. Okay, now here's why the constant is so important. Because at this point, if we have a constant, we're going to plug it in, just like we've done with these related rates problems all along. So I'm going to go ahead and be able to fill in tangent of theta is equal to A was not constant, so I leave that as the variable A, over 80 is side B, and that is the constant. Okay, now what we are trying to do is find d theta dt. So we're going to clean this up and just kind of get rid of the fraction here. So we're going to multiply both sides by 80. So we'd have 80 tangent of theta is equal to A. And now what we want to do is go ahead and take the derivative of this with respect to time. All right, and the reason this is going to work is because remember when we take the derivative of tan theta on the left-hand side here, theta, okay, we're taking the derivative with respect to t. And this t does not match this angle. And so when we take the derivative, we're going to have to use the chain rule. All right, so we're going to end up with a d theta dt. Okay, so we keep our constant, 80. All right, the derivative of tangent, hopefully you're saying it out loud, is secant squared. Keep the angle times the derivative of the angle, which is d theta dt. Okay, that's what a lot of students forgot last year. And if you forget that, then you're not going to have what you're solving for. So it's really important that you remember that d theta dt is equal to the derivative of A is dA dt. Okay, hopefully you're noticing what's happening now. All right, we have pieces that we can fill in. All right, so we know the dA dt, so you can go ahead and fill that in with 5. All right, d theta dt is what we're solving for, so I'm just going to leave that as d theta dt. All right, now obviously we have 80. Now what about the secant of theta squared, okay, secant squared theta? Well, we're going to actually get that, all right, from our trig ratio that we can find in our right triangle. It's saying secant of theta. Well, hopefully you know that secant is the reciprocal of cosine of theta. And so if I can recognize what the cosine of this angle is using the sides that I have in my triangle, then I can just take the reciprocal and use that fraction in my problem. So cosine, hopefully you know, is adjacent over hypotenuse. So that's 80 over 100, which I'm just going to go ahead and simplify. Obviously you know that would be 8/10, which would then simplify further to 4/5. Okay, so we have cosine of theta is 4/5, which must mean that secant of theta would be 5/4. Okay, so now I'm ready to go ahead and plug that back into the formula. So secant of theta is 5/4, and you're going to take that and square it. Okay, so now we're ready to go ahead and clean this up. So we have 80 times, this would be 25/16 d theta dt is equal to 5. All right, so we can go ahead and multiply this. Remember, this 80 is over 1, so 16 can go into 80 5 times. So I have 5 times 25, which is 125 d theta dt is equal to 5. Okay, one last step to get d theta dt by itself, and that's divide by 25. So I get 5 over 125, which is the same as 1 over 25. Okay, and that's the rate of change of the angle. Now, normally when we want to get our units of measure to finish this problem off, we would just go ahead up and we'd take whatever the unit was. But here we're talking about the rate of change of an angle. So when we do these problems, the rate of change, the unit of measure we're going to use is radians per, whatever the time that they're measuring, which this one was in seconds. So 1 over 25 radians per second is the rate of change of that angle. Okay, let's take a look at our second angle problem. The second one says a ladder 25 feet long is leaning against a house. All right, so I should be able to draw that right away. All right, so I have a ladder that's 25 feet long and it's leaning against the side of a house. The base of the ladder is pulled away from the house at a rate of 2 feet per second. So let's get some letters in here, okay? Obviously, 25 is our hypotenuse, so I'm going to call that C, and our other two sides will be A and B. So the base of the ladder is being pulled away. So here's the base being pulled away at a rate of 2 feet per second. So that tells me it's giving me a derivative, dB dt is equal to 2 feet per second, and it's moving in this direction. Find the rate at which the angle between the ladder and the side of the house. All right, so where's the ladder and where's the side of the house? So they're talking about this angle right here. Okay, find the rate at which the angle between the ladder and the side of the house is changing when the base of the ladder is 7 feet from the wall. Okay, so again, remember the base is the bottom, so the base of the ladder is 7 feet from the wall. And so they're giving us B here is 7 feet. Okay, so we have 25 feet for the length of the ladder, 7 feet from is the base of the ladder from the wall. And so I should be able to go ahead and find my third side. Well, this is one of those Pythagorean triples that you should memorize or commit to memory if you don't know it already. Okay, this is a 7, 24, 25 right triangle. And so we know that A then must be 24 feet. All right. Next question that hopefully you're starting to ask yourself is, are there any constants? Okay, do I know, are any of these constants? And so I'm looking at this, and I know that the ladder here is getting pushed away. And as the ladder gets pushed away down here, obviously it's going to drop here. Okay, so the ladder's getting pushed away. So the only constant that I have is the length of the ladder. That is secure. Okay, and so C, our hypotenuse, is our constant. Okay, so let's go ahead. We know we're going to be using C to build our formula to pick a trig ratio. So let's see what other one we're going to use. Which of the two other sides do I have more information about? Well, certainly, I definitely have more information about side B. So I'm going to be using side B and side C according to this angle up here. Okay, so which sides are those according to this angle? That's my opposite, side B, and side C is my hypotenuse. So which of the three trig ratios uses opposite and hypotenuse? Hopefully you're screaming, sine. So sine of theta is equal to side B over side C. Remember, first write it with the variables, then ask yourself which of those is a constant, and fill that in. So sine of theta is equal to side B over 25. Go ahead and multiply that 25 to both sides. So 25 sine theta is equal to B. Okay, at this point, you're going to go ahead and take the derivative of both sides with respect to t. So 25 comes down. Okay, the derivative of the function sine is cosine. Keep the angle times the derivative of the angle. So d theta dt is equal to the derivative of b, which is dB dt. All right, now we're ready to start filling some pieces in. So 25. Remember, where do I get the cosine of theta? Hopefully you're remembering that you're going to go back to the original. So cosine of theta is what? Cosine is adjacent over hypotenuse. So from my angle theta, which of these sides is the adjacent? That would be the 24, and which is the hypotenuse? The 25. So I'm going to be able to fill in that the cosine of theta is 24 over 25. Okay, times d theta dt is what I'm solving for, is equal to dB dt is what they gave me, 2 feet per second, so 2. All right, now let's clean it up. Look how beautifully this works out. The 25's just cancel, so I get 24 equals times d theta dt equals 2. Divide by 24 on both sides, so I'm going to get d theta dt equals 2 over 24, which is the same as 1/12, and that would be, again, radians per second. So there is the rate of change for that angle. All right, good job. Okay, the next kind of problems that we're going to tackle here are shadow problems. And what you'll notice is that as you're reading these problems, that they're all going to talk about somebody and their shadow as they are either walking towards a light source or walking away from a light source. And so what you're going to notice is going to happen is we're always going to end up with these similar triangles. So there's some things that I'd like you to remember about similar triangles and just some things that we're going to use in these problems. So first, corresponding parts of similar triangles are proportional. And that's going to be very important. That's something that you learned in geometry. And we definitely have to use its application here to do these problems. The second thing is that the person's shadow is going to be the base of the smaller triangle. So the next two things you're not really going to understand until we draw the pictures, but I just wanted you to get them down. And the third is that the tip of the shadow is the base of the larger triangle. Okay, so taking a look at our first example, it says, a man 6 feet tall walks at a rate of 5 feet per second away from a light that is 15 feet above ground, like a lamppost. When he's 10 feet from the base of the light, at what rate is the length of his shadow changing? All right, so let's get a picture and see what we're looking at here. So we have this lamppost, okay? And it's obviously giving off light, okay? And then we have a man, and it says he is 10 feet from the base of the light, okay? And so here's the man, oops. All right, and he is walking away from the light, all right? And it says it's talking about his shadow. Well, hopefully you know, where would the man's shadow be? All right, so as he's walking away, where's his shadow going to be? His shadow is going to be in front of him. If the light is shining down on him, his shadow is going to be right here, between like here and here. So I'm going to label that S, and I would recommend you do that as well. All right, and we know that he is 6 feet, and we know that the lamp is 15 feet. Okay, so we can label both of those. All right, I'm just going to go ahead and draw this in, and now hopefully you can kind of see where we're getting our similar triangles from. We have a triangle here, and we have the big triangle here. Okay, so we did find out that this distance between the man and the lamp, which we're just going to go ahead and call X, is 10 feet. Okay, so if we look at this problem, we see we're given a rate and we're asked to find a rate. And they both have to do with things on the base of this triangle on the ground. So if we look here, we are given a rate of 5 feet per second. And that's how he's walking. So which of these two indicates where he's walking? Well, I would say it's this one right here. Okay, and so basically that 5 feet per second is our dx dt. That's the rate at which he's walking. So oops, dx dt is 5 feet per second. All right, and then the question is, at what rate is the length of his shadow changing? So hopefully we recognize, and we talked about, that this is the shadow. And so what it wants to know is, what is ds dt? That's our unknown. Okay. Okay, at this point, it might be helpful to go ahead and just kind of draw this out as two different triangles. One would be our big triangle, and one is the smaller triangle. And so our big triangle has the left-hand side of the lamppost, so that was our 15 feet. Okay, our big triangle has this entire side as the base. So X and S make up the base. So if I wanted to combine those, I would say X plus S is the base of this triangle. Okay, our smaller triangle is just this portion right here from the man and his shadow. And so that would be the left-hand base, or the left-hand side there would be 6 feet. That's the man's height. And the base of that is just the S, just the shadow. Okay, so what some of you may recall here and recognize is that what we're given in these two triangles is similar triangles. And so if we want to go ahead, we should be able to set up a proportion with comparing similar sides, okay? The sides of similar triangles are in proportion. And so we should be able to set up that 15 over X plus S should be equal to 6 over S. All right, and so then what do we do when we have a proportion? Hopefully you recognize that you're going to go ahead and just cross multiply. So we have 15s is equal to 6x plus 6s. Okay, we're going to go ahead and combine things to one side. So that would be 9s is equal to 6x. And then what is it that we want to find? We want to find the rate of change of the shadow. So I'm going to solve for s in terms of x. So I'm going to divide by 9 and have that the shadow is equal to 6/9 x, which of course is the same as 2/3 x. Okay, so if I want to find ds dt though, I'm going to have to take the derivative of that equation I just came up with respect to time. So derivative with respect to time. So what am I going to get? ds dt is equal to 2/3 dx dt. And so ds dt, we're just going to go ahead and plug in the rate of change of x, which we have right here, is 5 feet per second. So 2/3 times 5 is going to be 10/3. And then we need a unit of measure, and that would be feet per second. And so the rate of change of the shadow is 10/3 feet per second. Okay, there was a second part to this question, and it said, at what rate is the tip of his shadow changing? So what I did is I just kind of redrew our triangle so we could look at that. And there is a really key word here that says the tip of his shadow. So if you don't know what that means, basically this is the tip of his shadow. All right, and so when it's talking about what rate the tip of his shadow, it's talking about this whole base, the larger base, okay? And so that is what the tip of his shadow, which makes the problem very different than the one up above. So we definitely need an expression for that entire side. So I'm going to go ahead and call this whole side just a new variable. Let's call it y. All right, so then what they want to know, the rate at which his tip of his shadow is changing, is they want to know dy dt. That's our unknown for this problem. All right, so I'm going to kind of redraw this again as two separate triangles. So I have my one larger and my smaller triangle. Okay, so the larger triangle has a side 15, and this one has a side of 6, a height of 6. Okay, and now my bases, well, I'm going to call this base the base of the green of the first triangle here, the larger triangle, with my new bottom, which is y. And if I'm calling that y, then what would I call this piece here? Well, I don't want to call it s, and why is that? Well, because I'm going to do this problem as if I hadn't done part A. And so I am going to do this problem as if I don't know ds dt. But what I do know is dx dt. And so I want to make an expression for this that uses the y and uses the x. And that would be y minus x. So if I take the whole length of the side y and I take away the x, that would be what is remaining here, or the shadow. All right, so now I can go ahead, now that I have that set up, and I can do exactly what I did with the last problem and write a proportion. So I have 15 over y is equal to 6 over y minus x. Okay, I'm going to go ahead and cross multiply by 15y minus 15x is equal to 6y. All right, so get the y's together. So I'd have negative 15x is equal to negative 9y. This time I'm solving for dy dt, so I want to get y in terms of x. So I want to get rid of the negative 9 here. So I'd have 15/9 x is equal to y, which of course is the same if I divide top and bottom by 3, as 5/3 x is equal to y. Okay, so now I'm going to go ahead and take that, and of course take the derivative with respect to time. So I would have the derivative of the left-hand side would be your 5/3 dx dt is equal to dy dt. So 5/3 times 5 equals dy dt. So 5/3 times 5 is 25/3. And then, of course, we need a unit of measure, and that would be feet per second equals dy dt. So the rate at which the tip of the shadow is changing, which is, of course, the whole base, is 25/3 feet per second. Okay, last one for the night. It says Julie, who is 5 feet tall, is walking towards a lamppost. So that should strike as a little bit different. She's walking towards the lamppost that is 12 feet high at a rate of 4 feet per hour. Okay, so same kind of idea. We have a lamppost that is 12 feet tall. Okay, and we have a girl, Julie, who is 5 feet tall. And this time she is walking towards the lamppost. Okay, and so now, and she's walking towards the lamppost at a rate of 4 feet per hour. So once again, I'm going to call this distance between the lamppost and Julie X, and I'm going to call this shadow, okay, from Julie to the end of her shadow as S. All right, and so we know dx dt is equal to 4 feet per hour. Okay, so now what is it they want? At what rate is her shadow changing? So the shadow, not the tip of the shadow, just the shadow, when she is 4 feet from the lamppost. So x here is 4 feet. Okay, so they want ds dt. All right, so let's take a look at this. Well, first of all, I do want to point out to you something really important, that because she's walking towards the lamppost, she's walking in a left direction, okay? And when that happens, our rate of change, it's like she's walking backwards. And so our rate of change here for dx dt should be negative. And that's going to be important as we work through the problem. So we want to make sure that we take note of that. If you are walking to the right, okay, that would be a positive rate of change. If you're walking to the left, which in this case, towards the lamppost, that would be a negative rate of change. And think about why that's happening, because what's happening with her shadow, as she is moving in this direction, her shadow is also going to be moving in that direction, and so her shadow is going to be decreasing, and therefore it should end up as a negative rate of change. So just kind of things that you want to keep in mind as you're progressing through this problem. All right, so once again, if it helps, you're going to go ahead and make yourself 2 triangles. Okay, one bigger than the other. So 12 and 5 are the heights of these triangles. Okay, the base of this triangle here is x plus s of the bigger triangle, and the base of the smaller one is just s. All right, so we can go ahead and set up our proportion. We would have 12 over x plus s is equal to 5 over s. All right, cross multiply, and we have 12s is equal to 5x plus 5s. All right, so let's get our s's on one side. So subtract 5s, we'll have 7s is equal to 5x. All right, remember, we are solving for ds dt. Okay, we want the rate of change of the shadow. So let's get s in terms of x. So we're going to divide by 7, so s would equal 5/7 x. Okay, take the derivative of that with respect to time. So ds dt is equal to 5/7 dx dt. Okay, plug in the dx dt that we were given. So 5/7 times -4. And so we end up with -27 feet per hour is your rate of change of your shadow. Now, if you notice, I just want to make something aware, and so you don't think you did anything wrong. In this problem, we really never needed to know how many feet she was away from the lamppost. And that was just extra information that was not necessary. It doesn't mean you did anything wrong. Sometimes they throw in extra information that you don't use. In this case, that 4 feet was not necessary in the solving of this problem. All right, great job. So we did 2 big kind of different topics today, so please make sure that you can separate those in your brain. We'll definitely be practicing both of those next time. And this ends our mini lessons here on related rates. So feel free to go back and relook at any of those videos. Make sure that you are on point with each of those different lessons. Thanks a lot and have a great night.